You ever wonder how we actually make sense of the world? How we find our way around? Well, it's not magic. It's something called spatial reasoning. And today, we're going to break down that powerful logic, starting with the absolute basics.
We've all been there, right? That split second of panic when you're not sure which way to go. But what's amazing is that for thousands of years, we've had this incredibly reliable tool right over our heads. Long before your phone, long before any paper map, there was the sun.
Okay, so let's get into this because it's super simple but kind of genius. Seriously, try this tomorrow morning. If you face the sunrise, boom, you're looking east. That means west is automatically right behind you. Then just stick your arms out. Your left hand will point north and your right hand will point south. And just like that, you've turned yourself into a human compass.
So that's awesome for figuring things out when you're standing in a field. But how do we take that same logic and put it on a flat piece of paper? Well, that's exactly what maps are for. They give us a standard way to look at the world.
And here is the golden rule that makes pretty much every map work. It's so simple. North is always up at the top, which means south has to be at the bottom, east is over to the right, and west is on the left. Let's put that to the test right now.
All right, puzzle time. Here's a little campsite map. We've got 4 tents, a road, and a lake. Your mission, should you choose to accept it, is to color in the tents using just these 4 clues and what we just learned about directions. Go on, give it a shot.
Okay, let's walk through it together. First clue, find the road. The tent to the west, that's to the left, right, is blue. Easy. Next, find the tent closest to the lake. That one's green. Now from that green tent, we look north, which means we look up, and that one's purple, which leaves just one tent, the one south of the lake, or down, and that one has to be yellow. See, it's all just simple logic once you know the basic rules.
So we've got pinpointing locations down, but what about getting from point A to point B? Let's level up from just finding spots on a map to actually following a route. This is where directions turn into a story.
Check this out. This is a bus route, but it's broken down into simple steps, kind of like your GPS does. You start at the parking area, you drive north, so straight up. Then you hang a right, heading east. Then another right turn points you south, and you arrive at your stop, S2.
Okay, now for a real-world problem. Take a look at the map. You can see Lolly's house right there. Now, just by looking at it, which bus stop do you think is actually a shorter walk for her? Is it S1 or is it S2?
And this is where things get really interesting. See, while the bus has to take that long, winding road to get to S2, Lolly can just walk a super short, direct path to S1. And that highlights a huge concept in navigation, the difference between the path distance, the roads you have to follow, and the straight line distance, or what people call as the crow flies.
Let's be honest, the real world is messy and complicated. So, to get around complex systems like a subway or a metro, we sometimes need a different kind of map. One that throws out perfect geography to focus on what actually matters, getting from A to B. This is what we call a schematic map. The distances are all wrong. The lines are perfectly straight. And that's the whole point. When you're on a train underground, you don't care if the track is curving. You just need to know 2 things. What's the next stop, and where do I need to change lines?
So let's take a trip. Say we want to go from Qutub Minar to the Supreme Court. A map like this cuts through all the noise. It just tells you what you need to know. Get on the yellow line, ride for 10 stops, get off at Rajiv Chowk, and switch to the blue line. Then it's just 3 more stops, and you're there. It makes a really complex journey feel incredibly simple.
So what's the big takeaway here? It's that this map's design boils a whole journey across a massive city down to one manageable number. 10 stops, change, 3 more stops. 13 stations. It's designed for clarity, not for geographic accuracy.
Okay, so we've gone from the sun to simple diagrams to these clever schematic maps. Now we're at the final level, the grid. This is the system that gives us mathematical precision, and it powers everything from your phone's GPS to the maps in video games.
So what even is a coordinate grid? You know what, just think of it like a giant game of Battleship that's been laid over a map. You've got vertical columns with numbers and horizontal rows with numbers. And by picking one of each, you can give any spot on that map its own unique secret code.
Let's use this zoo map as an example. You want to find the panda? Okay, you go to column 1, then up to row 1. Its coordinate is 1, 1. What about the lion? Well, that's over at column 3 and up to row 3, so 3, 3. The elephant? That's column 6, row 4. Every single spot has its own perfect mathematical address. And the rule for reading these is always the same. It's like you walk along the hallway, then you go up the stairs. You always go across the bottom first to find the right column, and then you go up to find the right row. Across, then up. That's the secret to finding anything on a grid.
So think about it. In just a few minutes, we've gone all the way from using our own shadow to find north to using a precise mathematical grid to find anything. These are all just systems, invisible rules for organizing information to help us navigate our world. And it really makes you wonder, doesn't it? What other invisible systems, what other maps are you using every single day without even thinking about it?